Welcome back to the deep dive. Today we're going somewhere pretty fundamental. We're aiming to really get under the hood of commodified gravity.
Yeah, this is a big one. It's framed as a unified field theory, but honestly, it's more than that. It's proposing gravity isn't what we thought it was at all. It's saying gravity is basically a side effect of quantum information.
A side effect of an entanglement, right? The idea that space-time itself isn't the stage, but something that, well, emerges.
Exactly. It emerges from this incredibly complex pre-geometric network. Think of quantum states all tangled up. And space-time is just the large-scale pattern we see. Like reality itself is being, I don't know, rendered.
Okay, so for everyone listening, our mission today is pretty ambitious. We want to unpack how this Qm theory, starting from entanglement, changes our picture of light, how it messes with our concept of time, and then what kind of, frankly, wild extrapolations does this lead to?
It's definitely ambitious and, it jumps right into the deep end by tackling maybe the biggest headache in physics right now, the cosmological constant problem, the CCP.
Ah, yes, the infamous 10-120 problem, where quantum theory predicts this enormous vacuum energy that should just gravitationally crush the universe, but, well, obviously doesn't.
Right. The observed cosmological constant, lambda, is just tiny in comparison. Standard physics basically throws up its hands and treats lambda as this weirdly fine-tuned number.
A fudge factor, essentially.
You could say that. But Quinn says, hold on, maybe we're looking at vacuum energy wrong. From an informational perspective, there's a limit. It suggests the gravitational effect of that vacuum energy gets capped by the quantum entropy of the vacuum.
So the amount of information the vacuum can hold puts a ceiling on how much gravity it can exert.
That's the idea. It's trying to derive lambda from fundamental principles from quantum entropy instead of just plugging in a number that fits observations, like the standard lambda CDM model does.
Okay, so it aims to explain dark energy's origin using quantum information maths.
Yeah, and that fundamental approach is what leads to maybe its most startling claim, the one that really connects gravity to everything else.
Which is the connection to light, right? That's the hook that got me. The idea that a theory about gravity can somehow predict the strength of electromagnetism.
Exactly. It claims it can derive the fine structure constant, alpha EM.
The constant that dictates how strongly light and matter interact.
The very one. Qmn argues alpha EM isn't arbitrary. It's a direct consequence of the universe's fundamental geometry at the tiniest scale specifically, its fractal structure. How chunky reality is determines how strong light is.
Wow. Okay, let's dig into that foundation. So the bedrock of Qm, this idea that entanglement is gravity and geometry is just what comes out of it. How do we even picture that? If geometry isn't fundamental, what is it?
It's the pattern. Think about the holographic principle. It's like the 3D world we experience is encoded on some lower dimensional boundary, like a hologram.
The information is on the boundary, the reality is in the bulk.
Right. And the Ryu-Takayanagi formula, the RT formula from ADCFT, gave this mathematical teeth. It showed that a geometric quantity, the area of a surface in the bulk spacetime, is literally proportional to the entanglement entropy in the boundary quantum theory.
So what you're telling me is that geometry isn't fundamental, it's just the pattern of quantum entanglement.
That's the core shift. Geometry isn't the stage anymore. It's defined by the relationships, the entanglement of the quantum actors. It really is it from qubit.
Okay, and Qmn turns this philosophical idea into actual gravitational dynamics. How does it modify Einstein's equations?
It adds a new term. The standard Einstein field equation, the EFE, basically says mass and energy curve spacetime. That's the two in term.
Right. Matter tells spacetime how to curve.
And spacetime tells matter how to move. But Qmn adds the entanglement correction tensor. So the equation becomes, well, more complex.
So now it's not just mass and energy, but also this Qmn representing the energy of quantum correlations.
Exactly. It's the energetic footprint of entanglement and coherence in the vacuum. Qmn gives this quantum information the same status as matter or energy in terms of its ability to warp spacetime.
So if the old EFE says mass warps space, the Qmn version is saying mass warps space, and the way the vacuum's information is structured also warps space.
That's a perfect way to put it. Qmn is a new source term for gravity, rooted in information.
Does it keep the cosmological constant term, the lambda part?
It does. The structure is Qmn-frac plus Qmn, so you still have that geometric vacuum energy term. But the Qmn part, derived from information and entropy via the first law of vacuum thermodynamics, acts to regulate or cap the huge vacuum energy contributions that standard QFT predicts would go into Qmn. Gravity becomes this emergent thermodynamic force.
Okay, let's pivot to how this connects gravity to everything, starting with light and this fractal holographic principle. What does a fractal spacetime actually mean? Smooth sheets are out.
Pretty much, at the fundamental level anyway. If you could zoom way, way down to the Planck scale, Qmn says spacetime isn't smooth. It's rough, self-similar, like a coastline or a snowflake. It's described by a network, a graph, with a dimension that isn't a whole number, a fractal dimension, d({.
So the smooth 4D reality we perceive is just the macroscopic average of this. Incredibly complex, chunky, fractal structure underneath.
Exactly. And the theory actually calculates a specific value for this underlying geometric fractal dimension. It connects log 3, which is about 1.8928.
Where does that number come from? It sounds very specific.
It comes from an informational argument. The idea is that there are 8 fundamental pre-geometric degrees of freedom in the underlying network, and these collapse or project down into the 3 spatial dimensions we see when geometry emerges. The ratio of the logarithms captures that transition.
Okay, so it's derived, not just picked. Now this connects to the fine structure constant through a constraint called scale invariance.
Right. The core constraint is that the quantum mutual information, basically, how much shared entanglement there is between 2 regions, has to stay the same, even if you zoom in or out by a specific factor.
And that factor is?
They use a factor of 10. The argument is that this connects the Planck-scale physics to our macroscopic base 10 observational world. Mathematically, this scale invariance constraint is expressed using something called the Pellis function. It's set this function evaluated at alpha EM equal to 1. So P alpha EM.
Wait, slow down. Why does keeping information consistent across scales suddenly spit out the strength of electromagnetism? What's the Pellis function doing there?
The Pellis function pops up in number theory related to sequences and scaling. Here it acts as a mathematical translator. It takes this physical requirement that the information structure must look the same when scaled by 10 and turns it into an equation where alpha EM is the variable. For that scale invariance to hold, alpha EM must have a specific value.
Hold on, you're saying that the strength of light's interaction, a fundamental constant, is determined by how chunky the universe is at the tiniest scale. That blows my mind.
That is precisely the claim. It's radical. Now, the underlying geometric dimension is the DFEF prox 1.892801. But when you look specifically at how electromagnetism propagates on this fractal structure, it experiences an effective fractal dimension, which the theory calculates as DFEM approx 2.9311.
Okay, so electromagnetism sees a slightly different chunkiness.
Effectively, yes. And when you plug that number into the formula derived from the scale invariance condition, which is alpha EF time DFEM.
What do you get?
You get alpha EF prox 1137.0367.
And the measured value is?
About 1137.035999 Gauss. The agreement is, well, it's startling. It suggests alpha isn't just some number we measure. It's dictated by spacetime's fundamental geometric and informational consistency.
Okay, I have to push back a bit here. This sounds almost too good to be true. How do we know this isn't just clever reverse engineering? Choosing the scaling factor of 10 using this specific Pellis function constraint. Couldn't that just be tuning the model to fit the known answer?
That's the million-dollar question, right? The proponents argue these choices aren't arbitrary. They claim the d-val value from the 8-to-3 collapse and the specific scale invariance condition are required for the emergent spacetime to be thermodynamically consistent, to obey things like the first law of vacuum thermodynamics we mentioned earlier.
So they argued the constraints are necessary for mathematical self-consistency, and alpha EM popping out so accurately is proof of that consistency, not the result of tuning.
That's the justification offered, yes. It's a strong claim and needs more scrutiny, but the numerical result is undeniably provocative.
Okay, let's move to the speed of light itself, c. If geometry emerges, does c emerge too?
Queen suggests yes. The idea is that c isn't fundamental either. It rises statistically. Think of underlying pre-geometric paths, maybe like 2D paths similar to Bohmian mechanics. These paths have some intrinsic quantum speed. When these paths get projected and averaged out into the emergent 3D spacetime geometry, the statistical process naturally imposes a constant speed limit, which we observe as c.
So photons are statistical phenomena, and c is like the average speed limit imposed by the emerging 3D road network.
That's a decent analogy. And it implies that maybe, just maybe, if we look closely, c isn't perfectly constant. We might see tiny deviations or effects not predicted by standard QED.
Like vacuum birefringence. What is that exactly?
Right. Vacuum birefringence is a predicted quantum effect where In extremely strong magnetic or electric fields, the vacuum itself acts like a temporary crystal.
Meaning light passing through it would split based on polarization.
Exactly. Different polarizations would travel at minutely different speeds. Standard QED predicts this effect, but it's incredibly small. Qmn, because of its underlying informational structure of the vacuum, predicts this effect might be enhanced.
And that's testable.
People are trying. Experiments like BIREF at HiBEF are designed for this. They use incredibly powerful lasers to create intense fields and then shoot high-energy X-rays through them, looking for that tiny polarization splitting. If they find an enhancement matching the Qmn prediction, well, that would be huge. Direct evidence for the vacuum's quantum structure.
Okay, so Qmn links geometry to light. Does it do the same for time? Let's talk about the thermal aspect. There's this alpha term in the Q-mensor that directly couples curvature to temperature. That feels like a massive departure from GR.
It is. It ties gravity directly to thermodynamics via the Unruh effect. You know, the idea that if you're accelerating, the vacuum around you doesn't look empty, it looks like a warm thermal bath.
Right. The Unruh temperature depends on your acceleration.
Qmn takes that and says, high curvature is like high acceleration. So regions of strongly curved spacetime, like near a black hole event horizon, or even just a very dense star, intrinsically generate a local Unruh temperature. Let's call it the Qmn-Tax.
So curved spacetime is inherently hot, not because there are particles moving, but because the geometry itself creates a thermal field due to the acceleration needed to stay put.
Precisely. And here's the crucial Qmn feedback loop. This temperature, generated by the curvature, it physically affects the underlying quantum network. It modulates the entanglement, how strongly connected the fundamental qubits are. More heat might mean less coherence, for instance.
Okay, so temperature changes the entanglement pattern.
And then here's the loop closing. That changed entanglement pattern via the Qmn tensor feeds back to alter the emergent geometry itself. It changes the curvature.
Wow. So curvature creates heat. Heat modifies entanglement. Entanglement redefines curvature. It's a self-regulating system. You mentioned the Bisonian-Witchman theorem formalizes this.
Exactly. BW provides the deep mathematical link in QFT between geometric boosts, related to acceleration in Rindler horizons, and thermal states. Qmn basically elevates this theorem from a mathematical property to a dynamic engine of spacetime.
That coupling constant alpha must be absolutely gigantic then, linking tiny quantum thermal effects to macroscopic curvature.
It's astronomical. The calculated value is around $72 times Tex K22. It highlights how sensitive the emergent spacetime fabric is to these underlying quantum thermal information dynamics. Even tiny tweaks could, in principle, have big gravitational consequences.
And this complex fractal thermal nature must mean time and space don't behave quite as smoothly as GR predicts, especially in dynamic situations, like with gravitational waves.
That's a key prediction. The fractal structure implies modified dispersion relations for gravitational waves. Instead of frequency being strictly proportional to wave number, Qmn predicts deviations, especially in high frequencies.
Meaning gravitational waves might travel slightly differently depending on their frequency, a potential quantum gravity signature.
Exactly. Something future detectors might be able to pick up.
Okay, this leads us straight into the most, well, sci-fi sounding part, gravitational control. If gravity emerges from entanglement and heat, can we engineer it?
That's the ultimate extrapolation the theory points towards. If gravity is tied to these underlying quantum properties, then manipulating those properties could manipulate gravity. Qmn identifies 3 knobs we could theoretically turn.
Knobs on the quantum vacuum, what are they?
First is coherence and phase relationships in the quantum network. Second is entanglement density, just how much entanglement there is per unit volume. And the third, which is crucial for dynamics, is entropy gradients.
Gradients. Differences in entropy across space. That connects to the beta term in Qmn, right?
Precisely. The beta term essentially says if you can create a slope, a spatial gradient, in the entanglement entropy of the vacuum, you can generate an entropic acceleration field. You can push things around not with mass, but with organized quantum information.
How on earth would you engineer an entropy gradient in the vacuum?
Well, the sources point to platforms we're already developing for quantum simulation. Things like optical lattices and Bose-Einstein condensates, BECs.
Why those systems?
Because they offer incredible control. With optical lattices, you can trap atoms in patterns of laser light, cool them to almost absolute zero, and then use other lasers to precisely control their quantum states, their spin, their coherence, and critically, their entanglement with neighbors. You can literally try to paint an entropy pattern onto the trapped atoms
So you'd create a small-scale, controllable entropy gradient in the lab.
and see if it produces any measurable gravitational-like effect, as predicted by the beta term. It's the very first conceptual baby step toward engineering spacetime.
Let's dig deeper into that beta term and its biggest claim, potentially replacing dark matter. How can an entropic force mimic the gravitational effects of vast amounts of invisible mass needed to hold galaxies together?
Okay, so the beta term, driven by this entropy gradient Nabla-Seiss, mathematically behaves a bit like a scalar field. It introduces an extra acceleration. The key is that this entropic acceleration becomes significant primarily in regions of very low intrinsic acceleration, exactly like the outskirts of galaxies where the dark matter problem is most apparent.
So it's similar in spirit to MOND, modified Newtonian dynamics, which also modifies gravity in low acceleration regimes. But here the source isn't a change to Newton's laws, but this underlying quantum entropy gradient.
Exactly. It aims to reproduce the flat rotation curves of galaxy stars moving faster than they should based on visible matter alone, not by adding invisible mass, CDM particles, but by adding this extra acceleration sourced purely by the vacuum's information structure trying to arrange itself.
No extra particles needed, just extra push from the quantum vacuum's organization.
That's the proposal, and it makes testable predictions beyond just rotation curves, particularly for how light from the early universe should be affected. That brings us to CMB lensing.
Right, the cosmic microwave background. How does Kuhn change how the CMB light gets gravitationally lensed by large-scale structures?
This entropic force predicts a specific, scale-dependent pattern of enhancement in the CMB lensing power spectrum. It suggests the lensing effect should be slightly stronger than predicted by standard lambda CDM, particularly at certain angular scales.
Is there a number associated with this predicted enhancement?
Yes, the theory predicts the overall lensing amplitude parameter Allen should be roughly in the range of 1.03 to 1.05. Standard lambda CDM predicts Allen should be exactly 1.
And what do we actually observe?
Interestingly, the Planck satellite data already shows a slight tension. The measured Allens is around 1.02 to 1.03, a bit higher than 1. Kuhn offers a natural explanation for this existing anomaly via the beta term.
But the key test isn't just the overall amplitude, it's the pattern across different scales, right? That's what distinguishes it from just tweaking lambda CDM.
Absolutely. Lambda CDM enhancements tend to be broadly scale independent. Qmn requires a specific bump or feature at particular angular scales in the lensing map. That scale-dependent signature is the smoking gun.
And we need better data to see that clearly.
Definitely. Eyes are on upcoming results from surveys like DDII, the Dark Energy Spectroscopic Instrument. If DKI's Year 3 data reveals that specific scale-dependent enhancement in lensing, that would be incredibly strong evidence for Qmn, really challenging the standard model.
Okay, so we have potential tests in light. What about testing Qmn through gravity and time directly? The sources talk about multi-messenger consistency.
Right, checking predictions across different cosmic messengers. One big one is the Hubble constant.
The Hubble tension.
The disagreement between early universe measurements, like from Planck CMB data, and late universe measurements, like from supernovae. Where does Qmn land?
Because the entropic acceleration term modifies the universe's expansion history slightly, Qmn naturally predicts a specific value for years SNPP. The calculation yields $8 Tₘₙ, approx 68.2 to Qₘₙ.
And how does that compare? It's remarkably close to recent measurements from large-scale structure surveys, like DSI, which found D$ approx 68.5 Tex/km/MMPa. It potentially resolves the tension by providing a value consistent with both early-ish large-scale structure and potentially late universe probes, unlike the conflicting values from pure CMB versus pure supernovae.
So could potentially fixes the Hubble tension, explains galactic rotation without dark matter, derives alpha EM. The coherence is getting pretty compelling if these tests pan out. What about the really exotic stuff like the gamma term and torsion?
Torsion. So standard GR assumes spacetime is torsion-free. It can bend and stretch, but it can't twist. The gamma term in Qₘₙ introduces torsion, linking it to the intrinsic spin of the underlying quantum constituents of the vacuum.
So detecting torsion would be like detecting the spin of space-time fabric itself. How would you even look for that?
It's incredibly challenging. It requires completely novel experimental setups. The paper suggests things like highly engineered mercury waveguides. Think of extremely sensitive, carefully constructed fluidic systems designed to resonate or react if a gravitational torsion wave passes through.
We're talking about building lab equipment specifically to detect the twisting fine structure of quantum gravity.
That's the frontier it points towards. moving beyond just observing the cosmos to actively probing the quantum nature of space-time in controlled experiments.
Okay, let's try to synthesize this. We've journeyed through Q-modified gravity, a framework that seems incredibly ambitious. It reframes gravity as emergent from quantum information, tackling huge problems like the CCP, the Hubble tension, maybe even dark matter, and claims to derive fundamental constants like alpha EM.
It really is a grand vision. It attempts to unify gravity, quantum mechanics, and cosmology, not by adding new particles, but by rethinking the fundamental nature of space-time itself, grounding it in entanglement and thermodynamics. The mathematical consistency connecting all these different areas is, I think, its most compelling feature.
So, looking ahead, what's the single most crucial test or observation that would really solidify Qin in your mind? What would make you say, okay, this is very likely how reality works?
That's tough because the consistency across multiple probes is part of the strength. But if I had to pick, I think seeing that specific predicted scale-dependent signature in the CMB lensing data from DISII would be massive confirmation of the entropic dark force. If that lines up and we get corroborating evidence for modified gravitational wave dispersion from Liga Virgo, or maybe even a hint of enhanced vacuum birefringence, the combined weight would be extremely hard to ignore. It really pushes us to look for the structure of information, not just new particles.
And if Qi is confirmed, the implications are just staggering. We started by talking about potentially engineering entropy gradients in BECs. If space-time is fundamentally controllable through quantum information, what are the limits? Could we genuinely manipulate geometry, maybe even time itself, in ways GR wouldn't even allow us to dream of? That feels like the ultimate, almost terrifying extrapolation here.
It opens doors to questions we barely know how to ask yet. If the fabric of reality is information, perhaps it's ultimately programmable. It's a profound thought to end on.